All right, I want to talk a little bit more about grammars today. Grammars. We were talking at the very end last time about converting NFAs and grammars back and forth. Now, only one sort of direction of that conversion is possible in general. You can convert any NFA into a grammar, and it's a very simple thing, and we don't need to belabor that. It's a very simple construction. At the end last time I was talking about, so maybe I'll just refresh our memory. Last time, any NFA can be converted to a grammar. Remember, grammar is that thing with like the arrows. That's not very descriptive, is it? Everything we talk about has arrows, but it's the thing with the substitutions, the grammar productions. Any NFA can be converted to grammar. The other way around is not generally true because some languages generated by grammars are not regular, so you couldn't possibly make an NFA out of them. But in some cases you can. So the best we can do as far as going the other way, grammar to NFA, this is a terminology that I said right at the end last time. Any single step grammar can be converted to NFA, and I will just refresh your memory what that means and how to do it. So single step grammar means something like S goes to BT or AR, T goes to AS or epsilon, R goes to AT or BS, something like that. This is called a single step grammar. And single step refers to the fact that every production, so in a single step, all productions look like sort of X goes to AY, or perhaps X goes to empty string, right? All of the productions where that little A, or it could be a B or whatever else, but just a single letter, all right? If that's the case, it's called a single step grammar. And this can easily be converted to NFA. The way to do it is you make ST and R are the states of my NFA. And then each single step production, the arrows in the grammar are called productions. Each single step production just translates directly into an arrow on the NFA. So S goes to BT just becomes this arrow, S to T with a B. It also says S goes to AR, so that's this arrow, S going to R with an A. It says T goes to AS, that's an arrow back this way with an A. It also says T goes to epsilon. Anyone recall from last time, how do you translate that into the diagram? T goes to epsilon. Yeah? Accepting state. Yeah, that means that T is an accepting state, right? T goes to epsilon basically means when you're doing these like substitutions to create a string, T goes to epsilon means like you can finish at this point, which corresponds to making T the accepting state. And then I have some more. R goes to AT, so that's like that, and R goes to BS like that. All right, so single step can be converted into an NFA. This is always easy to do if you remember, if you know how to do it. All right? Actually, we can do slightly better, even a little bit more generally than single step. This is called actually like a slightly more general, any what they call, these are called right linear grammars can be converted to NFA. There are many, many different sort of classifications of different types of grammars. Single step is a very simple kind of grammar. There's a slightly more complicated one called right linear grammar, and what right linear means is something like all the productions look like X goes to little xy, where this one is any string of terminals. So the only difference is it's not necessarily a single letter, but it has like several, it could be a whole string here, several letters at a time, not just a single letter. So here's an example of that. And once you see how this goes, it will become clear how to do it. It's not a complicated procedure. So this one is not single step, but it is what they call right linear. It's not single step because of this, for instance, ABA. If that were just a single letter, then that would count as a single step production, but it's not. It's several letters. Anyway, it's the same basic idea as the single step business, but we have to do something a little cute to accommodate for something like ABA. So in any case, we still have two states, S and T. All right. And when I see S goes to AT, for example, that's easy enough. That's just this, right? That's the second one here. We already know how to handle this. That's just a single step. What about this first one? S goes to ABAS. That's not single step. You have to do A, then B, then A, and get back to S. Now, don't write this down because it's wrong, but you may be tempted to do that. But this, of course, is not allowed in an NFA diagram because the arrows in an NFA must be labeled by one letter each. Anybody have a cute idea? I mean, you can kind of make something that acts like this. Yeah.
Just use like states.
Yeah. Let's just put, I think, two more states, and it's not even worth giving them names, but I want to do something like that. A, B, A. Right. So this has the same effect that I wanted. In order to get back to S, you have to do A, then B, then A. All right. You're not allowed to just put them all on a single arrow, but you might as well do that. It has the same effect. All right, and then, this is how we do the rest of it. So T goes to AAT. I do something like this. Right, that's another state. A little guy, you can make him big if you want. Sometimes I make them little. All right. And then I see T goes to S. That's just an arrow from T to S with the epsilon transition. That's the production T goes to S. And then T goes to epsilon, as usual, means that T is an accepting state. All right? So this is how we convert what we call right linear grammars to NFA. I got one for you all to try. This is essentially always easy. Once you know how to do it, you just do it. How about this one? S goes to ABS or BT. T goes to BBAS or AR or A squared. All right, see what you think about that one. This one has I'm throwing you a slight curveball. This A squared, you'll have to think about how to handle that. We actually haven't talked about that, but see if you can think of how to handle it. this is, I would write this as, this is what I read if it's like I was the BBT. And also T is the S. Good.
Does E squared make T terminal? It's a terminal.
It's something like that, but
So it's like A and then terminal.
I don't think you quite want that because that ends up back at T. Like for example, on a diagram you could do that twice. It would be like A to 4.
It would just be like A accepting.
Yeah, right. Yeah, yeah. All right. Yeah, all of this is good. You want something, this, how to handle that is similar to this empty string thing. So that makes R accept. This is kind of, it doesn't mean T is accepting, but it means if you do A, I think that should be accepted. Looks like everybody's doing fine. I'll write mine here. All right, can we discuss? My diagram is probably going to look different from yours, but so S goes to A, B, S. You should do like this, A and then B, back to S. S goes to B, T. It's just a simple B arrow like that. This T goes to B, B, A, S. That means you're going to make an arrow from T to S basically, but it has to have a B, then a B, then an A. So that's this. B, then A from T to S. T goes to AR is just one of those. T goes to A squared. People, as I was walking around, were figuring this out. This is basically, so if it said empty string, that just means R is accepting. I might as well put that in. But this is similar in that it represents the end of the grammar derivation. And so it does have to do with an accepting state, but it doesn't mean that T is accepting. It means that if you're in state T and then you do A, then it should be accepting. So the way to make that happen is like this. And accepting over there, right? Of course, if this were the empty string, I would just make T accepting by itself. But if it's some other string, you just sort of write out that string one arrow at a time and then make that accepting. All right, and then the R arrows, I need some more. R goes to BS, so that's here. R goes to ABT. I'll go out here. And I think I'm done now. Something like that. I hope you got something like that. Any variations? Your picture probably looks different, but. All right, great. Let's talk for about 10 more minutes, and then we go. I don't think we need to max out the clock. I had a long class this morning, like so it's 75 minutes. I went the whole time. I don't think they liked it. But I had for some reason I didn't plug my laptop in correctly last night. I blame my kids. They sometimes use the wire, plug in their they're Nintendos or whatever. But so my computer was very low battery when I started class, and I told them, like, it's probably just going to run out, and we'll just have to leave. But it ran out, like, right at the very end of scheduled time. So we weren't happy about that. You can watch the video from that class for a real cliffhanger ending, because it just immediately cut out right before I finished the problem. Okay, so we have talked about single-step grammars and right linear grammars. Those, as far as grammars goes, are very simple types of grammars because they can be back converted into an NFA, which means all they do is they make a regular language. The more interesting ones are ones which do not make regular languages, and there's still a big category of those that we are going to spend some time talking about, and they are called context-free grammars. And context-free grammars, the languages that they generate are called context-free languages. And this is sort of the next big category of languages that we're going to spend some time talking about. So the whole class, like before last week, the whole class was basically about regular languages. And from now, we are going to spend at least a couple weeks talking about what they call context-free languages. But I'll tell you about what does a context-free grammar mean. So a context-free grammar, this includes all the single step and the right linear. Those are all automatically context-free. Context-free grammar, which I am going to say CFG. This is one where each production has the form X goes to something, something, something. Maybe I'll just put like S here. Where the thing on the left is a single non-terminal and the thing on the right can be anything. All right. So all it means is the thing on the left of the arrow is just a single big letter, that's what all the examples we've ever talked about have been. If that is the case, then it's called a context-free grammar. So it just means the left side is just one letter. One big letter, right? A non-terminal symbol, the big S or whatever. All right? So all the grammars, certainly every one that we've talked about today, like this is context-free. It's because the ones on the left is just one letter. All right? This one is context-free. Everything that we've talked about so far today has been a context-free grammar, right? Something that's not context-free would be something like a non-context-free grammar would look like something like S goes to A, T, or T, T, T goes to B, S, B, or epsilon. AT goes to BBB, all right? That last one is what makes it not context-free. Now, this is allowed in a grammar. This is still a legal grammar, but it's just this one is not context-free grammar. So this one right here is what makes it non-context-free, all right? And the reason for this language about context, like what does all of this have to do with context? The idea is that a rule like something like S goes to AT, what that means is it means S can be replaced by AT wherever it appears. That's what it means when you use these arrows to create strings. If it says S goes to AT, it means if you ever see a big S, you can change that into an AT, this kind of substitution rule. All right? wherever it appears, all right? But a rule like something like AT goes to BBB, one interpretation of this rule, I mean, it still is just some kind of substitution rule, but one way that you can think about what this means. So this rule means that T can be replaced by BBB, but only when it's after A, right? You can think of a rule like that as representing some kind of thing where it says, yeah, the T can turn into a bunch of B's, but only if the T comes after a A. And that is to say, only in a specific context. That's where this word context comes in, all right? So you would say this production rule, it is a substitution you're allowed to do, but you're only allowed to do this in certain contexts. That is, in the situation when the T is preceded by a little a. Whereas a rule like this is context-free. That is to say, you can use this rule whenever you want. It changes a S into a AT, and there is no necessary context around the S. This is why this word context is used. Usually we're not going to think of it in this way, but that's why these are called context-free. All right? A language that is generated by a context-free grammar. A language generated by context-free grammar is called a context-free language. And we're going to write that as CFL. All right? So, we spent a month, 2 months maybe, talking about regular languages. There is a larger category, which includes all the regular languages, called the context-free languages. This includes the regular language because every regular language has an NFA, and every NFA can be converted to a grammar. And those grammars, if you follow the procedure that we use, are going to be context-free. All right? So these are called the context-free languages, and I will say any context-free language is a regular language, but not conversely. That is to say, there are some regular languages. I wrote it backwards. Sorry. Any regular language is context-free. I do this. Any regular is context-free, but not conversely. There are some context-frees which are not regular. For instance, A to the N, B to the N. That's everybody's favorite example. It is context-free because it has a grammar. This is the grammar. We had this example last time. This generates this language, A to the N, B to the N. And that is a context-free grammar because the left side of the arrow is a single letter. So it is context-free. So A to the N, B to the N is a context-free language. But as we all know, it's not regular. Right? And so I'm going to, for the first time, draw a diagram, which I'm going to draw many, many more times this semester. As sort of, this is referred to as the, there is a hierarchy. Sorry, I wasn't prepared to spell this word. Hierarchy, I think that's how you spell it. The hierarchy of languages. People who study this theory of formal languages or theory of formal computation is they talk a lot about this hierarchy of languages. And the smallest and the simplest type of languages are the regular languages, which I'll write as a little blob here. These are the regular languages. And then there is a larger universe of context-free languages. And there are some context-free languages that are not regular, right? And in particular, everybody's favorite example of that is, I will just write this, A to the N, B to the N, right? I put a little dot there. I'm thinking of A to the N, B to the N is like one particular example of a context-free language, which is not a regular language. What's an example of a regular language? I mean, obviously there's many regular languages. Something like A to the N by itself, that's regular, right? A to the N, B to the N is context-free but not regular. And it turns out there are larger and larger categories. And we're going to talk about, before the end of the semester, 3 more categories, at least 3 more larger universes of languages. There are things outside of the CFL category. I'll give you a hint. We will eventually talk about this. This is kind of surprising to me. A to then, B to then, C to then, it turns out, is too complicated to be expressed by a context-free grammar. You can make a grammar for this language, but not a context-free grammar. That is to say, if you want to make a grammar, you're going to have to do some funny business on the left side in order to make a grammar for that language. And then there are further larger categories, although I'll also tell you, A to the N, B to the N, you might say, okay, then it must be A to the N, B to the N, C to the N, D to the N. How crazy is that? Actually, that is no crazier than this. You can't get more crazy languages by adding more letters. But it turns out this kind of repetition of more than 2 exponents is really significantly more complicated to accomplish by grammars than repeating just 2 exponents. All right. I think maybe this is all that I'll say for now. This is sometimes called the Chomsky hierarchy. Any of you heard of this guy, Chomsky? This is a guy named Noam Chomsky, and he's a very he is a mathematician and linguist, and actually Chomsky invented grammars, this formal type of grammar that we're talking about. He is, I believe, still living, although just barely. He's super old, and I heard recently that he's not in good health, like just a few months ago. He's bedridden and non-verbal, unresponsive. So it's a shame about Mr. Chomsky. But he was a very successful and influential mathematician, but then he also became a bit of a political radical. I believe any of you know Noam Chomsky? Some people are like Chomsky disciples, like people sort of like build their life around the teachings of Noam Chomsky, not his mathematical. I'm more into his mathematical teachings, but I believe he describes himself as an anarchist, and he has all kinds of, shall we say, atypical political views. He's an American, but he's sort of viewed with skepticism by mainstream political folks. I don't know much about his opinions. He's an outsider. All right, anyway, that'll do it. So where we're going next time, we will just talk about sort of, I describe to you a language, can you make me a grammar for that language? And then the other way around also, I show you a grammar, can you tell me what it generates? All right, have a great break. We will have homework due, as usual, the Wednesday after the break. See you then.